So, Chapter 8, our analytic geometry in 2 dimensions. We've spent a couple of days talking about parabolas. And where on earth are we? Right here. So, when we did day 1, we got to this point where we saw this general equation in standard form that just looked like this big string of coefficients and variables with a's, b's, and c's and all that good stuff. And I talked about how we'll get to the point where our job will be to complete the square and figure out what is this? What form should this take? So with example 5, it says using standard forms with a parabola, prove that the graph of y squared minus 6x plus 2y plus 13 equals 0 is a parabola. And then we're going to find all the good stuff for it. So the vertex, focus, and directrix. And the way that we tell a parabola is, parabolas only have a y squared or an x squared. They don't have both. So when I look at this, and I know it says prove, but it's going to be an algebraic proof, where we notice, okay, if it has the y squared piece, it must have to look like this when we get done. That's the only way that's going to happen. And in order for us to get the y minus k squared, we're going to have to complete the square. That's how we do it, so that we can get a perfect square trinomial, and we can factor it into a binomial squared. Now, knowing that this is going to be the end product, I work towards that. So I make sure that anything with a y is alone on one side. So I'm going to leave the y squared and the 2y over here. But I need to move the other 2 over, because that has to do with x's and a constant, and since I'm pretty sure they didn't give us one that's absolutely perfect, I'm going to go ahead and move that constant over to the other side as well. So we add the 6x and subtract the 13 to get it over. Now, I know I have to complete the square and figure out a number that will make this work as a perfect square trinomial. So I have to go back to that teeny little formula, b over 2 squared from long, long ago. And notice that this would be my a, it's y squared this time, we're used to have an ax squared, but ay squared plus by, so that will be a 2. And 2 divided by 2 is 1, and 1 squared is 1. But whatever I add to this side, I have to add to the other side as well. So now, I have my y squared plus 2y plus 1 on the left, and a 6x minus 12 on the right. And I know I need to be y minus k squared, and that just means I've made my perfect square trinomial. Now I need to factor it as a binomial squared. Side, I'm supposed to have some number and then something about the x's. And so I realized, well, this is a great example for that one because I can pull 6 out of both of these. I can factor that out. So again, our 4p is a number that's going to sit in front of those parentheses. Well, now, that looks like a parabola. So I start thinking, I better start with the vertex. That's an important spot. And I have to remember, I always need to look for h and then k for the vertex. And h is back here this time, so that's going to be 2, negative 1 for my vertex. And I already know, because it's y squared, that it's right or left opening. Because this is a positive 6, I know it's going to open to the right. So I'm going to get my 2, negative 1 on there. And start to think about, that's going to open to the right piece. In fact, let me write that down. But I need to know, how far am I talking about from that vertex to what I need for the focus and the directrix? And that comes from the 4p equaling a 6. So 4p equals 6, well then our directed distance is 6/4, which reduces to 3/2 or 1 1/2. So knowing that it has to open to the right, I'm going to go to my vertex and go 1.5 units to the right and find my focus. And I have to write that down as an ordered pair. So the x value was at 2. I'm going to have to go 1.5 more, which would be 3.5. But you know we're supposed to use improper fractions, so we change that to 7 halves, -1 for the focus. And then the directrix, equal but opposite behind it, saying don't go this way, go the other way. So 1.5 units back would put me right here at x equals 1/2. And it didn't say we had to graph it, but it says prove that the graph, so it's kind of connected there, and I can't help but think, well, I know my focal width is 6, so I'm just going to go up and down 3 from my focus, and at least make a sketch. To show that that's what's going on. All right, did you get everything? This is my algebraic proof. Led me to, well, I'm going to say an obvious equation for a parabola. To anybody that studied parabolas, this would be an obvious equation for parabolas. And then we have vertex, focus, directrix. Even gave a nice little sketch over there, bless you, to finish all of that up. So when we get to the end of 8.3, the key to figuring out whether or not you need to complete the square to get a parabola or not is, this is the only one that has either x squared or y squared. So that's what we need to watch for. And it's one of those things that because we have more material to cover, sometimes people forget. So if you want to write yourself a little note somewhere in your packet there, the parabolas only have an x squared or a y squared, not both. By the time we get to the test, that can be something that you go back and flip through your notes and say, oh yeah, I have to remember. This is the one. Now we have the word probably part of our objectives, which is understand applications of parabolas. And parabolas happen a lot more in real life when you start to look for them. You know, almost everybody has a dish or something on their house to get their television going on there. So reflective property of a parabola is used all over the place. The main applications of parabolas involve their use as reflections for sound, light, radio waves, other electromagnetic waves. If we rotate a parabola in three-dimensional space about its axis, the parabola sweeps out a, and I love this word, paraboloid of revolution. So that's where we get our dish shapes from. If we place a signal source at the focus, which is absolutely what is done, you want to focus those signals so it comes in nice and strong. If we place the signal source at the focus of a reflective paraboloid, the signal reflects off the surface in lines parallel to the axis of symmetry, as illustrated in figure 8.9a, so this one right here. This property is used by flashlights, headlights, searchlights, microwave relays, and satellite uplinks. The filament is what gives it light. So when you push the button and the electricity connects, what it does is the light is actually shining at the paraboloid of revolution that we have here. But it concentrates it when it comes off, when it reflects off of those sides into one direction. So that's the difference between a floodlight and a spotlight. You know, this one is definitely a spotlight where you're going to get one piece here. Now for floodlights, which means you want to flood the whole area, this part of the light is shorter so that it'll spread out more. And it's usually flatter when you look inside of it. So that's how paraboloids work for flashlights, headlights, all that good stuff. Most of the time, like I said, we're seeing them as the principle working for signals traveling in the reverse direction. There's all kinds of signals out there all over the place to get your TV to work, you know, and they're digital now. So what you're doing with that paraboloid is you're trying to collect all of those rays and have them bounce off the sides to the focus. And the focus feeds into your system to tell it, hey, this is a station. I'm getting something here that's actually clear and going through. So that backwards piece is what we see when we're collecting up something as basic as a radio even. So this property is used to intensify signals picked up by radio telescopes, television satellite dishes, to focus arriving light in reflecting telescopes, to concentrate heat in solar ovens, and to magnify sound for sideline microphones at football games. And I can't help think this takes a little bit different road this year, as I'm sure you've heard in the news, there's talking a lot about UFOs now, and the belief that, yes, there are UFOs out there somewhere, and more pictures are coming out and all that good stuff. So they've been talking about signals for a long time, but more information has been released in the last few years than ever before. So definitely a field where more people will be finding jobs. Now, let's talk about studying that parabolic microphone. On the sidelines of each of its televised football games, the FB TV network uses a parabolic reflector with a microphone at the reflector's focus to capture the conversations among players on the field. If the parabolic reflector is 3 feet across and 1 foot deep, where should the microphone be placed? And we get a nice picture here. But the thought is, if I didn't have the picture, what would I do with this? Oh, we would absolutely put the vertex at 0, 0. Absolutely. That's the easiest place to work with any figure we're going to have. So we would absolutely say, you know what, my vertex is going to go at 0, 0, and I'm going to make sure that I put this halfway, perfectly centered at 0, 0. So that 3 feet across becomes 1.5 to the right and 1.5 to the left. And that 1 foot deep becomes its y coordinate. So if it's at 0, 0, and it's opening up, should I use an x squared or a y squared? X squared. But I don't need the h and k, because we're going to center it at 0, 0. That's what we want to do. So I start thinking, how do I figure out where that focus is? I mean, pretty obviously in the picture, that's what I'm supposed to do. And I realized that they didn't give it to me. It's not in the picture. That wouldn't be a good problem at all if they just flat out gave it to me. But they did give me something I could put in for x and y. Because of the way this is positioned, I have points on the parabola. I have 2 of them to choose from, pretty obviously. We'll use the positives because those are a little bit easier to work with. So we're going to put the 1.5 in for x, and the 1 in for y, and that will allow us to figure out what is that directed distance p. So we need 1.15 squared, which is 2.25, and then we'll have to divide it by 4, which I'm going to punch the whole thing in here anyway so everybody can see it. So 0.5625. So there's our p value. So now, if the parabolic reflector is 3 feet across and 1 foot deep, where should the microphone be placed? You notice I'm not going to even round this to the 3 decimal places here. I'm just going to go ahead and keep the 4 and be exact with this. But what I have to do is explain to them where that focus will be at. So, it's going to be on the focal axis. A distance of something from the vertex. Now the reason I'm saying something is because I need to go back and look at the labels and figure out if this was in feet, maybe I could give them a better idea if I change it into inches, that type of thing. So let's go back and see. 3 feet across, 1 foot deep, so this was in feet. definitely something I'd want to see in inches. So I could take my .5625 times 12. That's better. 6.75 inches from the vertex. So giving them an exact idea of what's going to happen. One of the other things this has been used for in the past, there was a really good problem in your Algebra 2 book about parabolas that you don't get to because you can't cover it in Algebra 2. It has to do with a solar hot dog cooker. And the book claims that people do that in Boy Scouts. Do you have any Boy Scouts in here? No Boy Scouts anymore. Yeah, they claim that if you use tin foil and you just go get like a piece of ductwork from Menards, that you can place a hot dog on the center so that it'll cook from solar heat. You know, and you won't have to make a fire. But I think most Boy Scouts would probably enjoy making a fire anyway, so I don't know that it's that useful. All right, that was what we had finished today. There is no graphing in 8183. You probably will need a sketch of a couple of them, but no graphing. Thank you for working without me yesterday. I'm dealing with a sore throat for 3 or 4 days now. That's it. So I know it's not COVID or anything like that. I was out working in my yard last weekend.